Hi, I'm Sanjay Manohar. This is a pre-recorded presentation for the 2021 meeting of the Society for Mathematical Psychology. I'm interested in the role of working memory. So to me, one thing is certain about working memory, and that is that it's not really about storing information, it's about using information. So we've got lots of models of working memory, slot models, bump attractors, activated long-term memory, but none of them include the use. In fact, they rarely even include readouts. So I'm going to briefly outline how we can go beyond storage models. So I'm going to suggest that working memory is really here to flexibly link up other representations, and it does this by creating rapid temporary bindings. And the whole point is that the memory contents can then change future responses. And I'm going to demonstrate this with three use cases. One is queued completion, so retrieval with a queue, that it can perform visual search, and that it can implement task rules. Now, a standard view is that working memory holds information, and a system can do this by having stable states for each possible memory item. So at rest, the system is stable, but at encoding, a stimulus pushes the system into one of these stable states. But after this, we have to do something. So a queue has to trigger a change in the network. For example, we might report what we saw. And this change has to be controlled by the contents of memory. In other words, the same queue stimulus, which I've drawn in this direction, must result in two different end states depending on what we just experienced. So these stable memory states must result in different trajectories. So what elements are necessary for a system to be able to do this? So when we think of neural networks, we usually think of the firing rates as the system's states. The dynamics, on the other hand, are governed by these weights. So let's say we're in one of these two memory states. Well, a queue pushes the system in a direction sort of drawn towards you here, and the simplest way to read out the content will be to have one state leading to one action and the other state leading to the other action. So the readout is on the y-axis here, and in the terms of Krishna-Shenoy, there is a null space, so any change within the horizontal plane is basically invisible to the actions. So these dynamics are not trivial, but they can be solved with a bespoke set of connections. I mean, you can train RNNs to solve this, as these authors have, but the issue is you would really need basically to tune a new pair of neurons for every possible combination of memory states and outputs. And I just don't think that's what working memory is. So here's a simpler way to think about this. I'm going to suggest that we can think of the synaptic weights themselves as actually being part of the system's state. So we could change the weights at the time of encoding, for example, to actually set up a new attractor. So here I've drawn a 2D plane, and this blue plane itself will correspond to just the firing activity. And notice that the response to the cue is basically entirely within this plane. But at encoding, the plane actually shifts to give a different response to the same stimulus. And the shift of the plane is actually a change in the weights. So I'm going to argue that working memory is best seen as setting up a new attractor so that the cue results in a particular trajectory. And this contrasts, of course, with the bump attractor models, where the feature units remain active and have fixed dynamics. So, for example, in visual working memory, one set of units might indicate the color of a bar, while another set might hold the orientations. And so instead of this, I'm going to incorporate some elements of an auto-associative network where the synaptic weights hold information even when there's no activity, a bit like in long-term memory. And so this means that new persistent activity attractors get carved into the synaptic weights by rapid plasticity to form associations. And so here's a highly simplified account that's deliberately implausible, but it's simple enough to see exactly what's going on. And I'm going to take visual working memory as the example here, and I'll assume there are just two types of neuron in the brain. So in the posterior cortex, when a neuron is active, it indicates that a particular thing is happening. So it might indicate a sensory feature, or it could mean executing a motor plan. It could indicate a concept or an abstract attribute. But crucially, these units are selective. So information is indicated by a pattern of activity. And in contrast, there are non-selective units in the prefrontal cortex, which are connected to all the feature neurons, but crucially undergo rapid synaptic plasticity bidirectionally with the feature neurons. In other words, through changes in these synapses, the selectivity of this population changes rapidly. So I'm just going to imagine there are 16 neurons, 12 of which are going to be feature selective, and 4 of which will be flexibly conjunctive. And we're going to have 4 different colors, 4 orientations, and 4 locations. And each stimulus will be a combination of these 3 feature domains. These neurons are connected to the conjunctive neurons by rapidly plastic Hebbian weights. So how this works is when a stimulus is presented, it activates the feature neurons, and these drive activation in the conjunctive neurons. These compete so that one wins out. And in fact, it generates a new stable attractor state where the conjunctive neuron sustains the object's features. When a new object is presented to the network, it disrupts the activity, but the synapses remain strong. So when a cue comes along, it reactivates the conjunctive neuron that was previously active, and in turn, this can reactivate the features of the object, causing retrieval by pattern completion. So we can say that Hebbian plasticity creates a path between the existing representations that guides the trajectory of activity, depending on what's in memory. So this network reproduces some standard working memory effects, including the set size effect, the serial position effect, the reaction time curve, and also the effect of decay over a delay. So we can extend this to continuous feature domains. So here we have units with smooth receptive fields. Otherwise the network is very similar, but it reports in a continuous domain. And when more items are encoded, we find that the model reports information with less precision. In addition to the precision, it sometimes reports the wrong item, what we sometimes call misbinding. So we made some surprising predictions about the effect of item similarity. It's easiest to see this when there are just 2 items. So in green here, we have our model predictions, and on the x-axis is the difference between the 2 items along the recall dimension. So in other words, it's the feature that's being reported. So when the items are very similar, the error is very small, and when they are very different, the error is large. And this is just because those 2 items are then predicting different responses. So it's exactly as you'd expect, and it matches the prediction of, let's say, Klaus Oberauer's interference model. But on the other hand, we can have a look at the similarity between the items along the probe dimension, and that's the feature that's used to trigger recall. Here we can see there's actually very little effect of the dissimilarity along the probe dimension. From our understanding of the interference model, we think that would predict a great increase in interference when the probe dimension is quite similar for the 2 objects. So we plotted out some of Sebastian Schneegen's data, and the effects of the recall dimension match what we predicted, really. But if we look at the probe dimension, well, When the features are both non-spatial, then it matches our prediction that there's very little effective distance. So, for example, retrieving the colour from orientation, vice versa. But if one of the features is spatial, then actually the predictions match really what you might expect from a pure interference model. And the reason for this in the model is just that when items are very close on the probe dimension, the probe feature drives strong competition because it lies very close to the watershed of two basins of attraction. We made some non-trivial predictions about serial order. The last item in a sequence actually sees much smaller distance effects than earlier items in the sequence. And this remains to be tested. Now, our cognition is flexible and we can follow completely new rules just on an instruction. Now, you're probably thinking this sounds like a job for plastic attractors. So we can just replace one of the feature domains with action plans. So when we encode a rule into working memory, we might activate a color like green and an action like left, and we activate them simultaneously, and this creates a conjunction with new stable attractor state, so that when a green cue is shown, then the left action gets triggered by pattern completion through this new trajectory that's been created. And this process models the whole decision process, including the competition between the attractors. And what this means is that responses are slower when there are more rules held in memory. And this matches Hicks' law. And because the attractors get strengthened each time they're used, that means that repeating an action actually makes the decisions faster. Finally, we can use a similar mechanism to guide attention. In visual search, we can encode a template into memory. So that's our search target. So for example, we might be looking for the color red. By activating the red units, we create a prefrontal neuron which is connected to all red features, this new conjunction here. And this results in two-way synapses which amplify items with matching features. So when the search array is shown, the red item preferentially activates the prefrontal neurons, and that gives them a reciprocal activation. So you can think of this conjunction as guiding competition between the object on the screen. And this predicts slower search with larger arrays. So as more items are on the screen, search is slower. When distractors become homogeneous, we find faster search matching the data. And when targets are repeated, we also find faster selection. Now, we also predict a fascinating new effect from Chris Oliver's group, which is when you have two search templates in memory, this can actually slow you down, but only when they compete to become active. And that's because the conjunctive neurons in our model compete with each other. Finally, the model can't suppress distractors, so it can't account for some of the distractor effects. So just to summarize, I've been thinking about how working memory actually gets used, and I've come round to thinking of working memory in terms of plastic attractors. And these kinds of representation serve to move the system into a new state based on a cue. So these cues trigger off events that depend on the contents of memory and can pattern complete. They can also be used to select actions or to guide attention. So by combining the rapid binding of new information using the synapses with the dynamic response to a cue, I think this class of network functions as a multiple demand network or as a global workspace. So, well, that's the idea. And I think we have to move from storage models of working memory towards thinking about working memory as providing trajectories that guide future states. Thanks very much for listening, and thanks very much to my lab.